All right, hello everybody. It's that time again. We're gonna do the next Physics 216 video. And today, what I want to discuss is bound and unbound orbits. So what have we worked out so far? So far, we've worked out that the radius of an elliptical orbit takes on this form, where if we had an ellipse and we're going to measure from one of the focus points where, say, the sun is, then we measure out a distance r to our planet, which is somewhere on the elliptical orbit, and this is the angle theta. Okay, so we also worked out what alpha and epsilon are. Alpha was this latus rectum, and it was ml squared over k, where k was the gravitational constant times the product of the sun's mass and the planet's mass. So over here is big M, and over here is little m. And L was the angular momentum divided by the planet's mass, and that's some constant. We also worked out an expression for the eccentricity, and it looked like this. It was a ml squared over k. So if you think back to what we did when we solved for this expression, what we had to do is we had to solve a second order differential equation. And when we did that, we got two integration constants. One was theta naught, and we got rid of theta naught by forcing r to be a minimum when theta was equal to 0. So I may have not drawn it perfectly, but the minimum distance from the sun to a point on the orbit is this distance r min when theta is equal to 0. We were still left with one integration constant, and it's this capital A. And so part of what's going to motivate this video is, can we figure out what A is related to, or more specifically, can we figure out an expression for the eccentricity epsilon in terms of only parameters that have physical meaning, not some integration constant A. And so the eccentricity, remember, this distance from the focal point to the center of the ellipse was the eccentricity times A, where A is the semi-major axis. Okay, so before we get on with it, I'm going to try something different here. I'm going to try to show you some slides, and let's see if I can make this work. I should have them loaded up. All right, good. So what I'm going to try to do is I'm going to try to plot orbits for different values of eccentricity. And so the first one I've plotted is an eccentricity of 0. So how did I generate this plot? We had just written down the radius as a function of angle theta. So if I want the x-coordinate, it's r cos theta, and if I want the y-coordinate, it's r sine theta. So I just picked some values for the eccentricity and a value for alpha, and we just calculate xy positions for theta from 0 to 2 pi. And if the eccentricity is 0, our ellipse becomes a circle, and not surprisingly, we get a circular orbit. So on the next slide, the eccentricity is 0.5. And you can clearly see that the sun, which is sitting at the position 0, 0, hasn't moved. Of course, I'm going to keep that the same spot all the time. And all I changed was the eccentricity, and we get this red orbit, which is clearly elliptical. We can make the eccentricity bigger, and so 0.9, and we get this purple orbit that's really elongated. Okay. And then we can do this case where epsilon is equal to 1. And if I expanded the x scale out to larger values of negative x, this blue curve, or cyan, or whatever the color is, would just keep extending out further and further. In fact, this cyan curve is a parabola, and it would never form a closed orbit. So the first three, the black, blue, and purple, are what I'm going to call bound orbits, and this cyan one is the first one where we see an unbound orbit, so the orbit never closes on itself. We could make the eccentricity even bigger, 1.1, and we just get another unbound orbit that just moves away from the sun at a higher rate, and then we could keep going. There's 1.5, and the blue one is another unbound orbit. And so what I'd like to do is I'd like to summarize those observations and then see if we can understand how we could deduce those results mathematically. So what do we know? Well, from those plots, one, by the way, those plots will show up on the course website along with a link, of course, to this video. So epsilon equals 0, we just get an orbit that is circular. So that's probably not surprising. 2. So we also looked at eccentricities that were between 0 and 1, and we got an orbit that is an ellipse. So I would call these two bound orbits. Okay, the orbit forms some kind of closed loop around the sun. These are bound orbits. All right, and then we looked at a third case where epsilon was greater than or equal to 1, and what we found is the orbit is unbound. So, I mean, that leads to a question. Maybe a couple questions. Is it possible for epsilon to be greater than or equal to 1? If so, under what conditions is epsilon greater than or equal to 1? Another thing we might do is we might say, well, it's all fine that we calculated these elliptical orbits for gravitationally interacting objects like planets and the sun in our solar system. But if you actually look at the planets in our solar system, we would see that, most of them are in these circular orbits. And so we could ask, under what conditions is epsilon equal to 0 such that the orbit is circular? Okay, so to understand some of these results, what we're going to have to do is we're going to have to do a bit of an energy analysis of the planet. So to understand bound versus unbound orbits, we need to examine the mechanical energy of the orbiting planet. I'm going to say planet, but it could be anything. It could be a satellite orbiting the Earth. Okay, so mechanical energy is going to be the kinetic energy plus the potential energy. And this is going to be equal to a constant. In the absence of dissipation, then there's nothing to take mechanical energy out of our system, and so that mechanical energy is going to remain constant. The kinetic energy is going to be 1/2 mv squared, of course, and the gravitational potential energy is minus k over r, where I'll write it down one more time just to remind ourselves that k is the gravitational constant times the product of masses. Okay, so let's think of, here's the focus, this is where the sun is, and then we measure out a distance r to our planet, which is somewhere along its orbit, and its velocity is tangent to this path, and here's theta. And so what we could say is that there are two components to this velocity. There is a component that's in the radial direction, and so that's going to be r dot r hat. And then there's a component that is perpendicular to r, so that's the theta hat direction, remember? And if we have rotational motion with a rotational speed of theta dot, then the speed out a radius r, a distance away from the rotation axis, is r times theta dot, and so this is r theta dot in the theta hat direction. Okay, so that's kind of a physical interpretation. We could just do that mathematically. I think we've done it already in previous videos, but v is going to be the time derivative of the position vector, which is r times r hat, and so that's r dot r hat plus r hat dot, but we already know that r hat dot is theta dot theta hat, and so our velocity is two components, r dot in the r hat direction and r theta dot in the theta hat direction. And so that corresponds to these red components that we just wrote down. When we calculate kinetic energy, 1/2 mv squared, we could calculate v squared as the vector v dotted with itself. And so that's r dot r hat plus r theta dot theta hat dot product with r dot r hat plus r theta dot theta hat. The theta hat and r hat directions are perpendicular to one another, so r hat dot theta hat is going to be 0, since r hat is perpendicular to theta hat. And then r hat dot r hat, of course, is 1, and theta hat dot theta hat is 1. Okay, so when you evaluate this dot product, we're going to get an r dot squared plus r theta dot squared. And so that's v squared, which we're going to use in the kinetic energy, 1/2 mv squared. So we already know something about theta dot, and what we know is that the angular momentum, little l, which is, angular momentum is big L, little l is the angular momentum divided by mass, and that was r squared theta dot, and that's a constant. That comes from conservation of angular momentum. So what we could do is we could therefore say theta dot is L over r squared, and we could take that and we could put that in right there. Okay, so then v squared is going to be equal to r dot squared plus, let's see, r times theta dot is going to be L over r, and then we have to square it, so we'll get L squared over r squared. Okay, so now this mechanical energy that we were trying to calculate is 1/2 m v squared. So v squared is r dot squared plus L squared over r squared. And then we have the potential energy plus U, which is minus K over R. Okay. Now remember, what we said is this mechanical energy is going to be constant no matter where the planet is in the orbit. So we can pick a special point. Let's pick our minimum. So let's consider either a bound or unbound orbit at r min. So what would that look like? If we had a bound elliptical orbit, then our r min is right here. If we had an unbound orbit, let's see if I can draw this, then here's the sun, and our minimum is right there. So in either case, if we were to draw the instantaneous velocity of our planet, let's say this was going in a counterclockwise orbit, its instantaneous velocity is tangent to the orbit, and at r min, there's no radial component. There's only a theta hat component. So v is in the theta hat direction, i.e. r dot is equal to 0 at r minimum. And the same thing is true even if the orbit's unbound. So whether the orbit's bound or not, the result here is the same. V is in theta hat direction. R dot is equal to 0 at r minimum. Okay, so if we go back to our energy expression, E is constant everywhere in the orbit. Therefore, E at r min is E at any other value of r as well. So all we're going to do is we're going to go to this expression here, and I'm going to set r dot equal to 0, and I'm going to set r equal to r min, and that must be what the mechanical energy is. Okay, so that means E is equal to 1/2 m. We're going to set r dot equal to 0, and we have L squared over r squared, and we're going to set r equal to r minimum. And then same thing in our potential energy, r is equal to r minimum. Okay, so let's compare this to what we know about our radius of our orbiting planet. So we know that r is equal to alpha 1 plus epsilon cos theta. And when we were deriving this result, we said that we were going to choose theta such that theta equals 0 corresponds to the minimum value of r. That's how we set the value of that constant, theta naught. And r is equal to r min when theta is equal to 0. Well, theta equals 0 just gives us a cos theta equals 1. So cos theta is equal to 1 when theta equals 0. So that means that our minimum is just equal to alpha 1 plus, divided by 1 plus the eccentricity. But alpha was ml squared over k. So that means our minimum is ml squared over k 1 plus the eccentricity. So the next step is just to take this expression for our minimum and sub it into there and sub it into there. Okay, so we're going to get an expression for the total energy of our planet-sun system is 1/2 m. We'll get an L squared and then 1 over our min squared. So that's going to give us a k squared 1 plus epsilon squared over m squared, and I guess it's L to the 4th, isn't it? And then we get minus k 1 over r min, which is going to be another factor of k, so we get a k squared 1 plus epsilon divided by m L squared. All right, so let's see, we can get rid of an L squared, and we can get rid of an m. So we get a 1/2 k squared 1 plus epsilon squared over ml squared minus k squared 1 plus epsilon m over L squared. Okay, so there's some common factors here. What are the common factors? We have k squared over ml squared. There's also a 1 plus epsilon we could factor out. I'm going to leave it in there. So we get a 1 plus epsilon squared over 2 minus 1 plus epsilon. Okay, so let's expand that square and see if we can simplify at all. K squared over ml squared. So we get a 1 plus 2 epsilon plus epsilon squared when we expand the square. And then I'm going to put everything over a common denominator. So we get a minus 1 minus epsilon, but I'm going to write it as minus 2 epsilon. And then I'll just divide everything by 2. Okay, so we get a 2 epsilon and a minus 2 epsilon. And we get a plus 1 and a minus 1, so we get a minus 1. And so what we've discovered is that the energy of our planet-sun system is going to be k squared k squared divided by, there's a 2 ml squared, and we get an epsilon squared minus 1, right? Epsilon squared minus 1. So the last step is to solve for epsilon. Okay, so 2ml squared e over k squared is equal to epsilon squared minus 1. And so therefore we get epsilon is equal to 2ml squared e over k squared plus 1 square root So here we go. Let me just quickly scroll back to the beginning, because what we started with was epsilon in terms of a constant a that we hadn't previously determined. And now what we have is epsilon in terms of only physically meaningful parameters. K is product of masses and gravitational constant. L is the angular momentum divided by the planet's mass. And E is now the mechanical energy of our system. And so all of these parameters have some kind of physical meaning for us. So this is the eccentricity of a gravitational orbit. This could be bound or unbound. In terms of energy. Okay, so we had a bunch of special cases to look at. So the special cases, the first one was a circular orbit. 1. Epsilon was equal to 0 gave a circular orbit. That's what we found from our plots at the beginning. All right, so I want epsilon equal to 0, so I could also say I want epsilon squared equal to 0, and the requirement is that 2ml squared e over k squared plus 1 is equal to 0. Okay, well, what does that mean? If we solve for e, we subtract the 1, so we have a minus 1. So we get minus k squared over 2ml squared. But k squared, let's start putting some of these things back in, is g times a product of masses. And then we have a 2m. L squared, so the angular momentum was m times r squared times theta dot. So if you divide by m, you get r squared theta dot squared. But if our orbit is circular, then anywhere in the orbit, the radius is a constant. So r is equal to a constant for a circular orbit. And if you remember, we calculated v squared, and v squared had an r dot term and an r theta dot term. But r dot must be equal to 0 for a circular orbit because r is constant, and that means the velocity v is equal to just r theta dot theta hat. Okay, so that means that what I could do is I could write theta dot is equal to v over r. Okay, so let's do that. Then what are we going to get? Our energy is going to be equal to minus gmm squared over 2m. And then we have r squared times theta dot, but theta dot is v over r, so we end up with r times v squared, so we get r squared v squared. Okay. What's nice about circular orbits is that they're pretty easy to analyze. So for a circular orbit, in fact, maybe what we could do is we could just work with the picture that we already have. The force on our planet, let me draw the planet in there. Here's our planet of mass m, and over here is the sun of mass big M. And so the force on our planet is just the gravitational force. And because it's in circular motion, we know that its acceleration must be the centripetal acceleration, v squared over r. And for a circular orbit, the gravitational force is equal to gmm over r squared, must be equal to the mass of the planet times a centripetal acceleration, v squared over r. Do some cancellation, and what we get is that v squared is equal to g times big M divided by r. Okay, so we make that replacement for v squared, and the energy is going to be minus g mm all squared 2mr squared. Okay, so 1 over v squared is going to be r g m. But now we have a g times m, and we have that squared in the numerator, and we have an r here and an r squared in the denominator. And what we end up with for our mechanical energy is just equal to minus, there's a 1/2, and what's left over is g m over r. But you might recognize g m over r. That's just the potential energy. Recall that the potential energy between like point masses, the one point mass being the sun, one point mass being the earth, is equal to minus g mm over r. And so what we found is for our circular orbit, the energy is equal to 1/2 of u. Circular orbit. But the energy, this is the mechanical energy, is just kinetic energy plus potential energy. And that has to be equal to 1/2 u, so we subtract off the u, and therefore T is equal to minus 1/2 of u. So what we found is a relationship between the kinetic and potential energy for an object in a circular orbit due to a gravitational field. If you were to go on and take, say, a third year or a more advanced mechanics course, what you might encounter is something called the Virial Theorem. This is an aside, so this is maybe not super relevant to exactly what we're talking about, but the Virial Theorem says that the average kinetic energy is equal to minus 1/2 of the average potential energy when the interaction, the force, is proportional to 1 over r squared. And so this is a very general theorem. It turns out that for our circular orbit, where the radial position is never changing, the potential energy is constant all the time. So the average potential energy is just equal to the instantaneous potential energy. And so that must mean that the kinetic energy is also never changing. So our planet in a circular orbit moves at a constant speed. So this is the Virial Theorem. So you might see that if you were to take at UBC Okanagan something like Physics 328. Okay, anyway, so the summary for circular orbits is the following. The eccentricity is 0. We require the energy to be 1/2 of the potential energy which means that the kinetic energy is minus 1/2 of the potential energy. Kinetic energy is positive, of course. This just means that the potential energy is a negative quantity. So we have minus a negative potential energy gives us a positive kinetic energy. It also means that our total energy is less than 0. So our total energy is negative. Let's do a little quick check. The check we can do is to see whether this result makes any sense. Kinetic energy is 1/2 mv squared. The potential energy is minus g mm over r. Okay, so we cancel the 1/2s, we can cancel the little m, and we can cancel these negative signs, and therefore we get v squared is equal to g m over r, and that should correspond to something that we've already calculated. So let's see if we can find it. Maybe I have, it must be in here somewhere. If I can't find it, I'll give up. Oh, here it is. So that's consistent with the result that we calculated just a page or two earlier. Okay, good. So that was circular orbits. Let's do case number 2, which is an elliptical orbit. So for an elliptical orbit, we want the eccentricity to be between 0 and 1. Okay, so this one will be less work actually. Although it seems like a more complicated case, the result that we want, we will get very quickly. So this was what we calculated for the eccentricity in terms of the mechanical energy. And we want this to be something that is less than 1. Now, let's consider what would happen. Well, okay, first let's make the following observation. All of the little mass m, the L squared, right? Anything squared is going to be positive, and k squared is just a bunch of constants squared. These are all positive constants. And so the only other thing that's in there is E. And so we have a bunch of positive constants times E plus 1. And we want to get a result for the eccentricity that is between 0 and 1. If E was positive, we would have a product of a whole bunch of positive things plus 1, and when we take the square root, we'd get something bigger than 1. And that would violate the requirement for the elliptical orbit. So it must be that E has to be negative in order to satisfy this condition. The only way to get an eccentricity between 0 and 1 is with E less than 0. And so this says that bound orbits require a total energy less than 0. In fact, that's consistent with what we found for circular orbits, because we already identified that for our circular orbit, our energy would be 1/2 u, but u is negative, and so that is a bound orbit, and so are our elliptical orbits, which all have a total mechanical energy that is negative. All right, case number 3 is could we have an epsilon greater than 1, which results in an unbound orbit? That's what we saw in the plots we showed at the beginning. Okay, so we write the same expression again. We have a bunch of positive constants times e plus 1, and we want that to be bigger than 1, so e better be positive, so that whatever we're adding to 1 is overall positive. So this requires e greater than 0, or positive. So unbound orbits require a total energy that's greater than 0, positive.